Hello Chem 213 students, and welcome to our first video for this week about Chapter 16, Conjugated Pi Systems and Pericyclic Reactions. So an interesting thing about molecules that have many alternating double single bonds, which as you guys know means there are sideways overlap p orbitals, the electrons get to move around. When they have many of these in a row, they tend to produce compounds that have a color. They absorb in the visible range. So for example, we have here the molecule Tyrian purple, which has double single, double single, double single, double single, double, and so forth. So it has a very extended conjugated pi bond system, which results in this purple color. And you can see many of these organic dyes are very valuable, and for example, Tyrian purple was meant to represent royalty in old times. Okay. So when this chapter is going to focus on conjugated pi bond systems, the simplest of which is a conjugated diene, meaning that they're in the structure, what you would witness is two pi bonds separated by a simple single bond here. And really what we know is that each of these carbons, 1 and 2 and 3 and 4, would have a unhybridized p orbital that is basically coming straight out of the page. And so these would allow for extended movement of electrons. This we refer to as conjugated, which you recognize by this type of pattern on double single bonds alternating here. If you have two double bonds, if you have a carbon with two double bonds, we call that accumulated situation, accumulated diene. If the pi bonds again are separated by a single bond, we call that conjugated. If they are more than one single bond away, they are isolated. Their p orbitals are not interacting, they're separate. So in terms of the overlapping of the unhybridized p orbitals, according to valence bond theory, when we have the accumulated diene, these carbons are sp hybridized. They have two unhybridized p orbitals. This one right here is rather in the middle. And so you can see one of those unhybridized p orbitals interacts with this unhybridized p orbital on this sp2 hybridized carbon. And then perpendicular to that, we have another pi bond with the other unhybridized p orbital on the central carbon with the single unhybridized p orbital, the sp2 hybridized carbon over here. Whereas if you have conjugated pi bonds, every carbon is sp2 hybridized. They all have one unhybridized p orbitals, and those p orbitals have this sideways overlap, leading to what we call conjugation. The electrons can freely move through this kind of electron highway made by these unhybridized p orbitals. Isolated pi bonds separated by a carbon here with two single bonds essentially. These pi networks are not connected at all. They're separated, so we call them isolated. So this chapter is going to focus on conjugated systems. When you have two double bonds separated by a single bond, you'll have a conjugated system where the p orbitals can have sideways overlap all the way through that region. There can be heteroatoms involved. Heteroatoms meaning atoms that are not carbon or hydrogen. That's like oxygen, nitrogen, sulfur, whatever. So here we have a conjugated diene that is really an ene-one. Ene for the double bond, one for the ketone here. Or for example, here we have nitrogen involved in this conjugated system. We have double, single, double, single, double, single. So this whole area here would be conjugated. And then over here, this one would be isolated. Conjugated. Actually, I guess that circle's a little too big. I should cut it off. These carbons. And then they're isolated by some of that, and rewrite that. So like these carbons are in the conjugated pi bond. This one's isolated here. So and when it comes to forming dienes, we can form alkenes by elimination. You learn that in chapter 7 of the textbook in the E2 reactions. And so if we use a base here, such as terbutoxide, on a halogenated alkene, that is allylic, one carbon bond away, we can get the diene here. Or if we have two vicinal alkyl halides here, like we have here, we can do a double elimination, get a diene. We would use the sterically hindered base, tert butoxide, to achieve these. Now, one thing to note about dienes is this single bond in a conjugated pi bond system is not like a normal single bond like you'd have between these two carbons here, because not only does it just have a sigma bond with direct overlap between orbitals like these two have, but it also has this extended pi bond network where each of these carbons is sp2 hybridized and the electrons can move all the way through. So the result is that really this bond is like kind of like a 1.5 bond. It has a shorter bond length and it has a stronger bond strength. It's because all these carbons here are sp2 hybridized with sp2 hybridized orbitals, which are smaller too. That shortens the bond length. But these are both sp3 hybridized carbons with larger hybridized orbitals. So you can see the size here. Basically, the more s character you have, the smaller the orbital it is. So an s orbital is smallest, then sp, and then sp2, sp3, then p orbitals. This was also important, remember, when we were talking about the stability of negative charges that reside in these orbitals, right? Being closer to the nucleus here, being smaller, and so forth. But these small hybridized orbitals, when they make sigma bonds, they make smaller, more energetic, harder to break, basically, more stable rather, not more energetic, but harder to break sigma bonds because the orbitals are shorter, and so everything is closer together. And so what we can see here is that if we hydrogenated this isolated pi bond to produce butene, we'd get 254 kilojoules out. But if we hydrogenate, if we do this twice, so this is 2 single bonds, compared to a diene where the double bonds are both on the same alkene, we have a lower energy that's released upon this reaction. And this goes to show you the greater stability of a diene versus 2 isolated alkenes. It's because of that shorter sigma bond here. So it's an extra 16 kilojoules per mole more stable. So here we have an example question. I recommend that you pause and try to decide for yourself how to rank these in order of stability, and then return. I will give you a hint. Remember, conjugated pi bonds are more stable. So the more conjugation, alternating double single that you have, the more stable the bond's going to be, or the molecule's going to be. So, okay. So you can go ahead and pause now. All right. So if you said that the most stable compound was D, you were right. So this has an extended conjugated pi bond system, double single, going across a total of 1, 2, 3, 4, 5, 6 carbons here. Okay. Now the least stable, so this is going to be number 1 in stability. The least stable, number 4, will be this one. It has 2 isolated pi bonds, so not particularly stable. And then lastly, we have to decide between B and C here. So with B and C, we're going to have to not only compare the conjugation. So here we have conjugation across 4 carbons here. Here we have conjugation across 4 carbons here. But we should also think about how substituted these double bonds are. Because remember, from our old chapter 8, from Chem 212, we said that the more substituted double bonds are more stable. And as you can see here, with this double bond, it only has this 1 hydrogen here. And this double bond has no hydrogens. So it's tetrasubstituted. Whereas here, and this one has hydrogen, this one has hydrogen. So overall, 3 hydrogens. Here, we have 1 and 2 and 3 and 4 and 5. So these are the more substituted double bonds here. And so these are going to be a little bit more stable, so this will be number 2. This one will be number 3. And so remember those two key ideas. More stability here for greater conjugation. Also more stability when pi bonds are more highly substituted with more carbon atoms attached and fewer hydrogen atoms attached. Also, you may recall that we would always say that sigma bonds, single bonds essentially, can freely rotate. But it's important to remember that in a pi conjugated system, this isn't exactly a sigma bond, right? The p orbitals are extending across this entire range. And so there's going to be a barrier to breaking this pi conjugation and reforming this other pi conjugation. So when we have a cis arrangement, in a sense, where the two double bonds are pointing towards the same direction here, in conjugation, we would call that S-cis. These two double bonds are pointing in the same direction. So it's not exactly like cis, like if you had this, this would be, and this was a double bond, you'd call this cis. And if you had this, you'd call this trans. Well, this is a bit different because we're not talking about the substituents on the double bond. We're talking about the double bonds themselves, right? So these double bonds themselves are positioned on the same side. We call it S-cis, whereas the double bonds positioned on opposite sides here, we call that S-trans. And in both cases, there's pi conjugation here, which must be broken to allow for the rotation. You have to break this conjugation for this to rotate and go into the other position. So the energy of the barrier of rotation here, it will cost 15 kilojoules per mole for this to go through this rotation and break the pi conjugated system here and make this newly formed pi conjugated system. But the thermodynamically, the S trans is more stable than the S cis. And so at any given time, if you have some 1,3-butadiene, that's what this is called, by the way, 1, 2, 3, 4, 1, 3, but for 4 carbons, diene, or the fact that there are 2 enes, so that's why there's diene, 2 alkenes, and they start on carbon 1 and carbon 3. With 1,3-butadiene, the S-trans isomer is more stable than the S-cis. The highest energy conformer is not conjugated. That would be basically the transition state between these. It's not really a transition state, but when it's in the middle of rotating, these pi bonds will not have their sideways interaction. And so it costs 15 kilojoules to get it out of this conjugated form, and so it can begin to recover 12 as a total of 27 kilojoules per mole to finally make the S-trans configuration. Now, as it stands up until now in organic chemistry, molecular orbital theory has been, I'd say, more confusing probably than it is useful. We've seen, examples of molecular orbital images here that show us bonding across multiple atoms that leads to greater stability. And where these molecular orbitals come from is from complicated quantum mechanical calculations. However, molecular orbital theory does become more important when we're talking about conjugated systems because it can really show how those molecular orbitals are extending across the entire conjugated pi bond system. So we have 2 orbitals here that get formed when we have 2 p orbitals here getting involved in being 2 p orbitals here getting involved in molecular orbital bonding. Here what we have is ethene to start with. Okay, and when we have ethene, then alkene, it's going to have 2 molecular orbitals. One where the electrons can freely move between, and this is the bonding orbital, and one where there's a node in between, which is opposing to bonding. There's no electrons in between for the pi bonding. So the molecular orbital here extends across the entire molecule. That's indicative of, in terms of valence bond theory, the sideways overlap of p orbitals, but in molecular orbital picture instead. So these 2 orbitals, these 2 p orbitals, each have 1 electron. So in total, those 2 electrons go into the bonding orbital, and you get a stable pi bond between these two carbons. But what happens now when you have a molecule like 1,3-butadiene, like this? Now we have all these carbons being sp2 hybridized. They all have an unhybridized p orbital, and so what you have on the left is the valence bond picture. So this is the valence bond picture, and this here is the molecular orbital, MOs. And so you kind of have a parallel between a situation in valence bond theory images here versus molecular orbital one. So the molecular orbital that is, in a sense, analogous to the sideways overlap of all these orbitals here is the one that extends across the entire molecule of 1,3-butadiene beyond all carbons. Okay. The other potential one is molecular orbital here is the one where there's one node in the middle, which corresponds to the sideways overlap of two p orbitals on one carbon versus the other, which are now in opposing directions. And there are 4 p orbitals here, each with 1 electron, right? Here's 1 p orbital, it has 1 electron. Here's 1 p orbital, it has another, and they're all sideways overlapped with 1 electron in them. So you have 4 total electrons, and those electrons in the molecular orbitals are going to be considered to be in the lowest possible molecular orbitals, right? These combination of these 4 p orbitals. The next higher energy orbital, which would be the one where we have an overlap between the p orbitals here in the center 2 carbons, but the opposite ones are not overlapping with anything; they're not involved. And then finally, the highest energy orbital is where each of these orbitals are not overlapping with one another. There's no overlap. There's nodes between every carbon atom which oppose bonding. And so the more electrons that go into these orbitals, the weaker the bonds become. So right now we get an extremely stable situation where we have essentially electrons that can go across all these p orbitals. And this provides stability to the molecule, this electron delocalization. Now, the 4 pi electrons, again, there were 4 pi electrons. They're going to occupy the lowest energy molecular orbitals. And so what we get here is kind of 2 situations. One where we're showing the electrons going across the entire molecule. We have double bond character across the entire molecule. So it's like we have the strength of the bonds in this perspective is double bond, double bond. But in fact, we also have this contribution here in which the center, there is no pi bond. So it's only 2 pi bonds. So this is more similar to what we'd be looking at, in terms of the perspective of the Lewis structure. It kind of shows, this is a double bond, this is a single bond, this is a double bond. This is kind of analogous to that. Double bond, single bond, separate double bond. But also contributing to this is this perspective of having essentially a 1.5 bond. Let me duck under this. A 1.5 bond all the way across the molecule, right? The electrons can go all the way through. And the reality is, it's a little bit of both. So molecular orbital theory, it's valuable even though it comes from quantum mechanics and the math is very complicated and we don't want to get into the math here. It offers a separate explanation for why the central carbon-carbon bond, the single bond, is shorter and stronger than a typical carbon bond, because this is kind of the picture of a typical carbon bond in a sense, right? Double bond here, but single bond in between. But really, the overlap goes across the molecule, and it's more like 1.5 bond. It's more like that picture of 1.5 bond, 1.5 bond, 1.5 bond. And so a 1.5 bond, or a partial pi bond along with your sigma bond, is going to lead to a stronger bond, right? And so this molecular orbital picture gives us a better kind of visualization of why this central bond is really no different than the other bonds, right? It's kind of like the electrons are moving all the way around. Not completely, though, because the second lowest energy orbital looks more akin to how we would draw it and think of it in terms of just looking at the Lewis structure. Now, the next one is for 1,3,5 hexatriene. So, just to go over the way the nomenclature works a little bit, triene means we have 3 double bonds, and hexa means we have 6 carbons in this thing. So, it's going to be 6 carbons 1, 2, 3, 4, 5, 6. On the first carbon, there will be a double bond. On the third carbon, there will be a double bond. And on the fifth carbon, there will be. So, this is 1,3,5 hexatriene. Okay. And we can do a similar analysis of the potential overlaps in the p orbitals. Again, because these are alternating double bonds, all these carbons here, they're all sp2 hybridized. So they all have an unhybridized p orbital. They all have an unhybridized p orbital. There are 6 of them. And so the molecular orbitals here, there's kind of 2 perspectives. The one that's more like the valence bond theory type perspective, the other that's more like the molecular orbital theory perspective, but we're referring to what molecules would go in these molecular orbitals. So we have the lowest energy molecular orbital is the one where we're kind of showing a 1.5 bond all the way down. 1.5 bond, 1.5 bond, 1.5 bond, 1.5 bond, 1.5 bond. And so the electrons can move freely through this p orbital, unhybridized p orbital highway here, providing greater stability to this molecule. The next less stable molecular orbital picture here would be the one where we have on half the molecule we have molecular orbital extending through that half, and then the other half we have a molecular orbital, and we have a node right in between the two. And so we have overlap between these 3 p orbitals and overlap between these 3 p orbitals. Next, we have the one where we have kind of looks a lot like the Lewis structure, right? Basically, what looks like a double bond, none of them interacting. Then we start to get to the unstable, the less stable. It's kind of like the dividing line here. These are the more stable ones. These are the less stable ones with a lot more anti-bonding. And so next higher energy here is we have kind of like 2 double bonds basically in single bonds on the end, no interaction of the p orbitals. Here we have just 1 overlap here, and then the least stable one is no overlap between the p orbitals. And there are 6 p orbitals with 6 electrons, so those can all go into these bonding orbitals and make, a kind of situation where we have electron distribution across all of these carbons. So the reason why we go into molecular orbital theory, and one of the reasons why it's so valuable, is because thinking about molecular orbital theory helps us to describe a lot of the chemical properties of these conjugated pi systems and also their physical properties. What we're going to see here is that this conjugation leads to a difference in energy between the what's called the HOMO, or the highest occupied molecular orbital, and the lowest unoccupied molecular orbital. And the amount of energy required when the pi conjugation system gets very large, the amount of energy required to promote an electron when light is absorbed from the highest occupied molecular orbital to the lowest unoccupied molecular orbital and reach this so-called excited state begins to lie in the visible range. And so this is how we get organic dyes like the Tyrian purple that I had shown you at the beginning, is because if we have extended pi conjugated systems, the gap in energy between the HOMO here and the LUMO starts to get out of the UV range and into the visible range. So one thing that we want to talk about here are reactions as well of these conjugated dienes. And these reactions are going to have an analogy here to the addition reactions that we learned in Chapter 8. And so recall from Chapter 8 that addition reactions begin with the nucleophile here, the pi bond here, also able to grab a proton here from a hydrohalide. So this is a hydrohalogenation addition. And then we get the leaving of these 2 electrons on the bromine to allow for a bromide ion. This carbon now, this hydrogen will attach here. So this carbon will have 3 bonds to carbon and no lone pairs. So it will be a carbocation. And then you'll have a nucleophilic attack of the bromide there. And remember, because this is a flat carbocation, we have not indicated the stereochemistry here. This would be racemic, right? You would get a mixture of both stereoisomers in here. Okay. But with a conjugated diene, it's a little bit more complicated because, like before, we're going to get a proton transfer here, but that's going to lead to a carbocation intermediate. And that carbocation will be on the more substituted carbon. But then we have a allylic carbocation, which we know is a structure here that has resonance. And so we're going to have to consider the resonance when we do the products. And this is something we actually also talked about a little bit in chapter 8 and had some examples of. So the result is that when we get this carbocation intermediate, as I've drawn here, so we have proton transfer, we have the bromide ion, but we have a carbocation here, and that carbocation is allylic. So it undergoes resonance here. And so here's a resonance arrow showing the movement of these electrons here. Now this carbon is still sp2 hybridized. It has 1 hydrogen attached, but it's making 3 bonds with no lone pairs, so it has no formal charge. Now note that this carbon here had 2 hydrogens attached, right? So it still has 2 hydrogens attached. And so it is now having 3 bonds and no lone pairs. And so it is sp2 hybridized. Is a carbocation because it has 3 bonds and no lone pairs. And so at that point, the bromide could attack either location here. So we've got both of these resonance structures now, the ones that we had before. The bromide can attack at the position right here, the more substituted position, giving you a so-called 1,2 addition, where the bromine, the hydrogen attached to carbon 1 here, the bromide attached to carbon 2. Or you could have a carbocation rearrangement before, and then the bromide will attack at this carbocation here, and this will be the 1,4 addition. And we call that the 1,4 addition because if this is carbon and number 1 here, 1, 2, 3, the bromine is attached to carbon number 4. But here, if it's carbon number 1 where the hydrogen attached, there will be the bromine attaching to carbon number 2 there. So we'll get a multitude of products here. And remember, on top of that, if you have a chiral carbon like this one here, you're going to get a racemic mixture of products, right? But however, in this case, this carbon is not chiral because there's 2 hydrogens. So that's something to keep in mind, is the stereochemistry as well. So when you do an addition of a hydrohalogenation, you'll get 1,4. You'll get a competition between 1,4, 1,2, and 1,4 addition. That's also true when you do a halogenation. So a halogenation begins in a similar, although not exactly the same way. So you have the bromine, which, because it is polarizable, is large and the electrons can move around. You have a potential that you can have a nucleophilic attack on the bromine, and then here we have the halogenation. Now, when you do that, of course, you get this bromonium intermediate, and this itself is like a carbocation essentially. We could say it's not exactly right. Remember, this does go through actually a bromonium intermediate, but we could say that in this bromonium intermediate, it's more bonded to this carbon here. It's less bonded to this one here, because it can carry the positive formal charge a little better, or partial charge here. And essentially, you can treat this instead more like a positive carbocation, and then you can get the same type of situation here. So in this case, you can have a 1,2 adduct the bromide can ultimately attack here at the second position, or you can have a carbocation rearrangement and the second bromide here will attack for the same reasons as the 1,4 hydrohalogenation. So this also occurs with the hydrogenation. Just remember the stereochemical constraints here, in that we'll get an anti-addition. Now, when it comes to deciding whether you're going to get the 1,2 or 1,4 adducts, this is going to be a competition between thermodynamics and kinetics. So we're going to take a look at the energy diagram here, but just to look at the results here, when the reaction is done at a colder temperature, such as 0 degrees Celsius, you'll get more of the 1,2 adduct and less of the 1,4 adduct. However, if you raise the temperature to like 40 degrees Celsius, you'll then get more of the 1,4 adduct and less of the 1,2 adduct. And so let's analyze the diagram to explain why that is. Well, the initial reaction is always going to be the proton transfer, and it's going to produce this carbocation intermediate. However, when it comes to the ultimate production of the 1,4 adduct versus the 1,2 adduct, the involved transition states are going to have differing energies here. And so when we look at this guy right here, it's going to, we have the nucleophilic attack here. That would produce the 1,2 adduct. This is going to be a more stable transition state here. So if the temperature is low, that's going to be favoring the 1,2 adduct. However, the 1,4 adduct will be produced when the carbocation is over here, and so the bromide is going to be attacking right here. This produces a higher energy transition state. You can imagine why. I mean, part of it is that you have to have more of this partial positive charge on a less substituted carbon. It's almost like a primary carbocation versus a second. So of course this transition state is going to have a higher energy. However, the final product produces a alkene here that is doubly substituted versus one that is singly substituted. So it's a thermodynamically more stable product. So if the temperature is higher and a sufficient number of molecules have the activation energy to get over this, you'll get more of the 1,4 adduct. So the 1,4 adduct, again, is the less substituted alkene, so it's less thermodynamically stable. However, it's kinetically favored because the intermediate is lower in energy, and the transition state leading up to the production of the product, rather. However, the more substituted product is more thermodynamically stable. So if the temperature is higher, more of the molecules will have sufficient energy to reach the higher energy transition state, and they will produce the more thermodynamically stable product. So at higher temperatures, the reaction is under thermodynamic control. It will produce a more thermodynamically stable product. However, at lower temperatures, the reaction is more kinetically controlled and will produce the product that has the more stable transition state. So it's just following up on that, the 1,2 adduct will form faster. Not only to the stability, but just due to the proximity too. That's another contributing factor, is that when you have the proton transfer occur, the bromide ion will already be pretty close to that carbocation that's produced at the second carbon, and so it can go ahead and attack. And it's already, that's also kinetically favorable, bringing those product and reactant here, these two reagents, in close proximity to one another, whereas the bromide will have to travel over here after it is the HBr is deprotonated to get over to the fourth carbon, which will be kinetically less favorable. So at lower temperatures, the reaction is under kinetic control. The reaction is more irreversible, and it's just going to produce that product that will result from the nucleophilic attack on the original carbon at the second position, right next to where the deprotonation happened. At higher temperatures, it will be under thermodynamic control, producing the more stable product, as I mentioned previously. One more thing to mention here is that when it comes to polymerization involving dienes, so there's a different type of polymerization that can occur with dienes that doesn't occur. So when we talked about polymerization before, it was radical polymerization initiated with a radical initiator, and it went forward with a different mechanism. One type of polymerization that we can have is with alkenes, however. And that when we have that polymerization, what will occur is that we'll get single bonds between each unit. So you can imagine the electrons here kind of moving and going into creating a sigma bond here to the next unit. And then these pi electrons here, this leaves a carbocation here after that. And so these pi electrons here will be allylic to a carbocation, and they'll need an extra place to bond because note this has 2 hydrogens, right? So if this one's going to bond over here, it's still going to have 2 hydrogens. And so it's going to need that extra bond to have 4 bonds here. And then this would continue. The next one would do the same thing. And it would go on, and you get this right here. We can do this with chlorine too. So this produces natural rubber here from isoprene, which is a common natural product of many plants. Or this chloropropene here, or chloroprene here, which would be called 2-chloro-1,3-butadiene. This one can polymerize to produce so-called neoprene, which many gloves are made out of. And so at that point, that's going to conclude my first part of my lecture here, covering chapters 16.1 to 16.5 of the textbook. And when we come back, we're going to start to talk about pericyclic reaction. I'll see you on the next one.